Okay, hello everyone. Welcome to session 9 of FRB 2021. It's been a phenomenal meeting already, and we're looking forward to a bunch of very interesting talks today. My name is Shami Chatterjee. I'm a research scientist here at Cornell University. That is actually my background, about 10 minutes away from here. For this session, we'll have a couple of recorded talks and the rest will be live. So just as a reminder, please do put questions for the presenters in the QA and I will try to get to them at the end of the talk. If not, also please use the Slack channel FRB 2021 Plenary 09 and we will tag the participants so that they answer questions there. Okay. I think with that said, let's get right to it. So the first speaker this session is Shivani Bhandari at CSIRO Astronomy and Space Sciences in Sydney, Australia. She is going to do this presentation as a recorded version. So take it away, Shivani.
A very good morning, good afternoon, and good evening, everyone. I am Shivani Bhandari, and I'm a postdoctoral fellow at CSIRO in Sydney. Today, I'm going to talk to you about FRB host population. I should mention that this work was done in close collaboration with RealFast, Craft, and FO teams. So I will start off by introducing 3 new FRB localizations and their host galaxies. With these new observations and also including the published FRB data, I will compare a larger FRB host galaxy sample with the underlying field galaxy population. Following that, I will present a differential analysis of the host galaxies of 2 apparent FRB's host population. I will then compare the global properties of FRB host with that of extragalactic transients, and also compare FRB offset distributions with galactic sources and also with globular clusters in late and early type galaxies. Finally, I'll present my conclusions. So we have heard a lot about FRB 180301 in this conference now. This FRB was originally detected by the Parkes Radio Telescope and later in sensitive follow-up observation with FAST, it was observed to emit repeating burst. So to localize the burst, we conducted a follow-up campaign with the VLA real-fast system in L-band and were successful in catching the source during action. A repeating burst from this FRB source was detected with a signal to noise of 19 in the real-fast 10 millisecond image at a DM of about 536 parsec per cubic centimeter, of which Milky Way ISM contribution is about 152, and the contribution due to IGM and foreground halos, which we call DM cosmic, is estimated to be 289. So now the burst is localized with a great precision of less than an arcsecond, and it's observed to come from outskirts of a star-forming galaxy, which is at a redshift of 0.33. The plot here shows R-band Gemini image. The association is pretty secure with a path posterior probability of 99.9%. Next, FRB 191228 was discovered during craft observations with ASCAP at 1.2 gigahertz. The discovery was made at the DM of 298 parsec per centimeter cubic. Offline interferometric analysis led to the localization of this burst, and guess what? The FRB sightline seemed to accompany the lonely star Fomalhaut. Thanks to the heroic efforts of some of our collaborators in craft, we were able to get rid of most of the glare from this star, and we were so excited to see the host in the VLT Forest 2 I-band and G-band images. We are confident about the association with a path probability of 100%. Again, this FRB is observed to come from the outskirts of its host. Spectroscopy observations from Keck telescope confirm the host redshift to be 0.2, and the galaxy has a stellar mass of about 5.4 times 10 to the power 9 solar masses, and has a very low star formation rate of 0.03 solar masses per year. Next, FRB 2009-06 was detected at ASCAP with a signal to noise of 19 at a DM of 579 DM units with an estimated DM cosmic of about 324. We localized this burst with an accuracy of about half an arcsecond, and the host was initially identified in pan stars, and then we followed it up with deeper observations with the VLT. So no big bright stars in the way this time, and we found the galaxy is an order of magnitude massive than the previous ones, and the star formation rate is half solar masses per year. So combining these new observations of FRB hosts with published data, we accumulated a sample of 16 FRBs with secure host association following the criteria of path probability greater than 90%. We also include M81, which is a host of another repeating FRB, and ASCAP FRB 171020 due to its low probability of chance associations. So our final host sample consists of hosts of 6 repeating and 10 non-repeating fast radio bursts. So with this larger sample, we first compare the host population with the underlying galaxy data from Primus survey for galaxies which have a redshift less than 0.5, so it's basically in the same range as that of FRBs. So plot on the left here presents the current star formation as a function of the stellar mass. Most of the FRB hosts lie in or around this star-forming cloud of galaxies, but are offset from this purple line, which is the star-forming main sequence. We also note that only 2 of our 16 hosts lie in the region occupied by quiescent galaxies. Now, plot on the right here show a color magnitude diagram and provides information about the overall stellar population in these galaxies. So the late type galaxies, which have ongoing star formation, have therefore younger stellar population, and they lie in this blue cloud. And then you have massive early type red-ended galaxies, which are lying in this red zone characterized by very low star formation rate and therefore older stellar populations. So we call them red galaxies. And then you have green valley galaxies here. So we see that the host galaxies of FRBs appear to lie on the luminous end of this absolute magnitude distribution, mainly near the blue cloud and green valley region, where galaxies are expected to be transitioning between a star forming to quiescent system. So now this is the same plot, but here what I've done, I have weighted the Primus data, which is in the background, by its stellar mass. So while this plot shows you where most galaxies are, the plot here is a close approximation of where most stars are in the local universe. So in this, we see that majority of FRB hosts do not trace massive galaxies, and they also do not seem to align with the color magnitude diagram space of the peak of the blue galaxies. So to quantify this effect, we examined the null hypothesis that FRBs track stellar mass. For doing this, we used the double Schechter function to model the galaxy stellar mass function for all, and then for star forming and passive galaxies, which are in the redshift range of 0.2 to 0.5. So we took a weighted cumulative version of this function and then compared that with the observed FRB host mass distribution. So our KS test shows that FRB hosts do not track stellar mass. Moving forward, next we tested the null hypothesis that FRB host tracks star formation rate. So we used the star formation rate distribution function derived from the UV and IR luminosity Schechter functions for the local universe using the Galaxy data. We then computed the star formation rate volume density distribution function and took a cumulative version of this function and then compared that with the star formation rates observed for our FRB hosts. And again, our KS test suggests that FRB hosts do not track star formation rates. Thus, we conclude that FRB hosts have lower stellar mass and star formation rates than randomly selected field galaxies, which are weighted by their stellar mass and star formation rate. So this implies FRBs track some other property. In this slide, next, we plot the famous BPT diagram, where the nuclear emission line ratios are used to determine the dominant source of ionization in a galaxy, and it also distinguishes between the star-forming liners and AGNs. We observe that FRBs are not drawn from a specific class and found the star formation and linear emission to be the ionization sources in FRB host. I should also note that all three repeating FRBs that we have plotted here are on the star forming side of this diagram, but they are not lying on the star forming main sequence. So next we performed a differential analysis of the host population of repeating and non-repeating FRBs. So we compared their stellar masses, star formation rates, projected offsets, absolute magnitude, specific star formation rates, and metallicities. And we found no statistical significant differences between the host of these two apparent FRB populations. Then we went on comparing the global properties of FRB host with that of other transients, such as ultra luminous X-ray sources, long gamma ray bursts, short GRBs, core collapse supernovae, superluminous supernovae, and type 1a supernovae, which are also proxies for accretion-induced collapse of white dwarfs. Then, following the method described in Bochnek et al., we also corrected for redshift evolution by scaling the stellar masses and star formation rates of each of the host galaxies to be statistically representative of Z equals 0 galaxies, because now we are comparing hosts of SGRBs and LGRBs, which can be at higher redshifts. So our results, we found that FRB hosts are statistically indistinguishable from hosts of core collapse supernovae and short gamma ray bursts. ULX and type 1a supernova projected offset distributions were found to be consistent with that of FRBs, but their host masses and star formation rates are statistically different from FRB host. So while from the host galaxy consideration, we could statistically rule out LGRBs and superluminous supernova for all the FRBs, we did find some similarities between repeating host population and hosts of LGRBs and superluminous supernovae. So these may be because of smaller sample size or the effect of R1 on the overall repeating FRB host populations, and definitely further investigations are needed to explore this effect. Next, following the work of Chimes et al., we compared the host normalized offset distributions of a larger sample of FRBs in their host with that of galactic sources, such as pulsars, magnetars, low and high X-ray binaries. So with our KS test, we couldn't reject the null hypotheses that these are drawn from the same underlying distributions. And finally, motivated by the discovery of an FRB in a globular cluster, we compared the host normalized distributions of FRBs with that of globular clusters in late and early type galaxies. So we use the published globular cluster data associated with spirals such as M81, M31, and elliptical galaxies such as NGC821 and NGC4278. We note that here M81 data is mostly dominated by the disk population of globular cluster, where majority of the clusters are within 10 kiloparsec from the galaxy centers. And for others, we do see a mix of disk and halo population in the data. So when we compare their distributions with FRB host distribution, we observe that FRB offset distribution is mostly statistically not consistent with offset distribution of globular clusters with 95% confidence. However, there are some caveats, such as we know globular cluster frequency scales with the stellar mass, and the FRB host population spans 4 orders of magnitudes in the stellar mass. And also in the current FRB host sample, it shows deficiency of elliptical galaxies. So definitely a much larger sample of precisely localized nearby FRBs are required to pursue this further. Talking about future, we are working towards upgrading the current craft system, which does the incoherent sum searches of FRBs at the moment. So the craft coherent upgrade, or CRECO, will enable fully coherent search via fast imaging of visibilities. And this is going to make ASCAP 5 times more sensitive than the current system in place. Thus, in the coming future, ASCAP will be delivering an FRB every day with Arcsecond localizations. And also, we are excited to announce that we have been awarded 180 hours of VLT time to observe 50 ASCAP localized hosts in the coming year. So please watch out this space for most host galaxies. And yeah, I will leave you with my conclusions here and happy to take questions. Thanks a lot for your attention.
Spectacular. That's phenomenal stuff. We don't have Shivani online, but we do have Casper Heinz online. Casper, if you are happy to answer some questions.
Yes, definitely.
All right. Let's see. We have one in the chat, one in the Q&A from Brian, and he comments that this is spectacular. Hard to believe we already have plots like this, and I heartily second that. It's amazing to see nice plots of this sort. Brian's question: what observational selection biases are there in the CDFs?
Yes, so I'm assuming it's the selection bias in the optical follow-up of the host galaxies. So I think currently it's hard to really quantify, in the sense that the FRB and the host galaxies we've observed has been like a mix, so the FRBs have been detected from various, like a wealth of different facilities, and it's not really, the selection function is very convoluted and more interesting bursts, and mostly repeaters have been followed up. So definitely it's hard to really quantify the selection bias, but we can also put it the other way. We have also been able, at least for now, to follow up everything that we could accurately localize. So that's working in the other direction in some sense. But that's the goal with this with our VLT survey, is to select 50 FRBs detected from one single facility, and then follow up everything. So provide a complete sample of FRBs and their host galaxies.
Okay. Another question from Jason in the chat, and he asks whether there have been any attempts to investigate whether host type and position correlates with FRB properties. Besides the obvious repeater, non-repeater dichotomy, are there correlations with large scattering or fluences or anything of that sort?
Yes, we have worked on that. So for now, we are mostly, of course, limited by the small number statistics, and so we haven't found any very obvious trends or anything, or we also consider DEM scaling with the stellar mass, for example, the star formation rate. Yeah, so no obvious trends have been found, but mostly likely due to the small sample size.
And related question, Zorawar asks, any inferences on the metallicity of these galaxies?
Of the metallicities?
Yeah.
Yes, we have, so I think for a little more than half, maybe even 3/4, we have been able to derive the oxygen abundances from the emission lines. So we have the total integrated metallicities of these galaxies, and they are typically range from like half solar to even above solar metallicities, but mostly follow the local mass metallicity relation.
Okay, and one last one we can squeeze in. Mohit asked, amazing talk, but he's curious about whether you've accounted for multiple testing hypotheses in the statistical analysis, that you're testing multiple hypotheses.
In what sense? I mean, so the only thing we've done with this sample is that we make sure to correct the FRBs and also the extragalactic transients to analyze their host galaxies, assuming they were located at the redshift 0, and then we just compare or use the regular KS test to.
Right. I think you might be asking, and Mohit, please feel free to clarify this in the Slack afterwards. He might be asking whether a statistical hypothesis testing question, where if you test multiple hypotheses, does that lead to some loss of significance in your detections?
I don't know. It's not something we have done, so I couldn't answer that.
It is worth following up in the Slack.
Yes.
Okay, well, thank you, Casper, for stepping in for Shivani to answer the questions. And again, this is phenomenal, fantastic work.
Thank you.
All right,
let's party in the background.
No worries. All right, let's move along. And our next speaker is Alexandra Mannings, an NSF graduate fellow at UC Santa Cruz. And she's going to talk to us about a characterization of FRB environments using high resolution imaging. So Alexandra, take it away.
Okay. Can you see that all right?
That sounds good. I'll give you a 12-minute warning.
Okay, thanks. Well, hello, everyone. I'm Alexandra Mannings. And as Shami said, I'm at University of California, Santa Cruz, working closely with F⁴, fast and fortunate, FRB follow-up, and craft. And today I'll be talking about a characterization of FRB environments using high resolution imaging. So this study utilizes imaging from the Hubble Space Telescope. Why do we use HST? And that's because it provides high resolution imaging. For example, in the infrared, we get a resolution of about 0.13 arcseconds per pixel, and for the UV, about 0.04 arcseconds per pixel. And the Hubble also allows us to get very deep imaging of these hosts so that we can study low surface brightness features that are otherwise not easily studied from ground-based imaging. And these in conjunction with one another allow us to study the kiloparsec scale local environments around these FRBs. So here I'm showing an image presented in Heinz 2020, which is a ground-based VLT image of the host of FRB 1910-01. And as you can see, there's a sort of, hint of the extension of spiral arms and other features going towards the FRB localization, which is in the black circle there. But with the sort of limit on the depth of the image as well as the resolution, we're not able to really get the best look at the local environment around this FRB. So that is why we use HST imaging. It really starts to bring out those low surface brightness features. We see now sort of more of a full picture of kind of the radius of the host, as well as the spiral features, all of that stuff. So we get a bit more insight into that local environment, or the kiloparsec scale environments. So I'm just going to quickly kind of scroll through all of the images that we presented in this study. On the left, you'll see the UV images, and on the right are the infrared images. This sample included 8 hosts, 6 of which were newly imaged, which are the ones that I'm showing you now, and then 2 were previously published hosts of 121102 and 180916. So first we take a look at the morphology of the hosts. We use GalFit to fit 2 CSIRO models to the host light, and then we subtract those models off and we get residual images. So here I'm showing the original images, and then here are the residuals. And this allows us to get a better look at the low surface brightness features, at the morphology of the hosts. And in this, we're able to see that 5 of the 8 hosts in this sample show a spiral structure. And not only that, but the FRBs appear on or very near to the spiral arms. And this was a very exciting result for us to come upon. And we actually got a little bit of press for this. This image was processed really nicely by someone at Alyssa Pagan at Space Telescope. And here you can really see the spiral structure really jumping out in those residual images, and then the localizations of the FRBs too. So that was very exciting. We also take a look at the radial offsets of the FRBs. So what is the distance between the center of the galaxy and the FRB localization? We set up a 2D Gaussian PDF along the semi-major and semi-minor axes of the localization, and we take a weighted average as our offset measurement. So here, just showing that value in arcseconds, in physical units of kiloparsecs, as well as the effective or a host normalized offset, which allows us to normalize across different host sizes. So showing 2 different examples here, one 1906-08, which you've also seen in Chatiti et al., and 1907-14. This has a bit higher offset, whereas this localization overlaps a bit with the center of the galaxy, and then also goes a bit to the edge. So we plot a CDF of all of the measured values. The gray region here is bootstrap estimated RMS. So we take into account the size of the sample size, as well as the error on the individual measurements. And we plot this CDF in comparison, as you saw, similar to Shivani's paper, as well as Casper, plot this in relation to other transients. So we look at gamma ray bursts and different types of supernovae. So the median value for our offset is about 3.2 kiloparsecs, and with testing the null hypothesis that they're coming from the same underlying population, we reject long gamma ray bursts and superluminous supernovae based off of the KS test. We also take a look at the host normalized offset CDF, the median for this being 0.9 effective radii. And with this, we reject the calcium-rich transients, and once again, long duration gamma ray bursts. So the offsets we seem to be getting are pretty moderate across all of these FRB and their hosts. We also take a look at fractional flux, which is a measurement that sort of looks at the brightness of the pixel, where the FRB is originating from in relation to the flux of the entire host. So these values are kind of like percentiles, or at least that's how I like to think about them. Where is this pixel testing in reference to the sort of brightness of the other pixels? So this 0.39, just meaning that 39% of the host light is in pixels fainter than this pixel. And again, we use the same 2D Gaussian weighting scheme and take the weighted average to be our fractional flux value. So again, doing the same CDF and KS testing. And this one-to-one line pretty much just says anything that follows that one-to-one line follows the stellar mass in the host galaxies. And so we see type 1a supernovae and core collapse supernovae following pretty closely to that one-to-one line. And then again, based off of the KS testing, we reject short gamma ray bursts and long duration gamma ray bursts. We know that short gamma ray bursts come from very, very faint or pretty faint regions of their hosts, whereas long gamma ray bursts are concentrated to the brightest regions of their hosts. And in this sample, we don't really see FRBs being in either really bright or the most faint regions of their hosts. Okay. And then again, sort of along those same lines of tracing the stellar mass, we look at the fraction of light enclosed. We do some isophotal fitting to the host galaxy, and the isophote that's closest to the radius or the offset of the FRB. We measure how much light is enclosed within that circle versus the entire sort of flux of the galaxy. And we find that this distribution is consistent with the radial distribution of stellar mass, as you can see, sort of, we're pretty closely tracing that one-to-one line as well. And yeah, I guess I may not have specified, but the fractional flux CDF that we were looking at before was infrared light. So looking at the stellar mass distribution, and here also looking at infrared flux. We also take a look at the local versus galactic environment in terms of stellar mass and star formation rate, surface density, local values versus the global values. And here we're looking at the stellar mass surface density, this one-to-one line, just saying that the local value is not, elevated in reference to the global or host value. And many of, or pretty much all of the hosts in this sample are close to or along this one-to-one line. And we also plotted a average value for Milky Way giant molecular clouds as reference. And then taking a look at the star formation rate surface density, many of these points were upper limits that we could place using the UV imaging that we got from HST. And many of these upper limits are very near or close to this one-to-one line. And then again, for reference, we plot some values for star-forming clouds here in the Milky Way, the Lupus clouds and Perseus, which you can see are very elevated in comparison to the global host value. And then same for 121102, we know that this FRB originates from a region of elevated star formation in its host galaxy, and so it's well above this one-to-one line. But for these others, we don't really see this elevated star formation rate surface density.
3 minutes, Alexandra.
Okay, thank you. And then finally, we place luminosity limits on, I guess, two different things. The first is whether or not there is some satellite galaxy at the same redshift as the putative host that we've associated this FRB to. And those limits you can see as the upside down triangles. And we use the luminosity of FRB2021 as a reference point because we don't really expect these FRBs to be originating from anything fainter than that host of 121102. And then based off of the dispersion measure of the FRBs, we're able to sort of extrapolate out towards to higher redshifts of a possible background galaxy or something that's not apparent in the image. And we're able to place a luminosity limit on a possible host at a higher redshift. And again, this is shown as the diamonds. And many of these points are below that luminosity limit that we've sort of placed at the luminosity of the host of FRB201102, except for these two 1910-01 and 1907-14. But again, we don't really expect these FRBs to be hosted in galaxies that are much fainter than 121102. So we think that it's unlikely that the FRB is coming from some satellite or a background galaxy that is not apparent in these images. And this is just an image of 121102 as reference. That again, it's a pretty faint host. So some takeaways. We conducted the first population study of FRB host galaxies using Hubble Space Telescope. We found that the FRBs were moderately offset from the host centers. We also saw that this sample of FRBs did not favor areas of particularly elevated or decreased stellar mass, nor star formation rate. 5 out of the 8 hosts show apparent spiral structure. And lastly, that it is unlikely that there is a background or satellite source that is the true FRB host. And I can take questions now.
Oh, fantastic. Absolutely gorgeous stuff. Very, very nice. Question and answer. I had a question for the previous talk as well, and that relates to this one. I'll go ahead and ask that while we wait for more questions to come in. What's your thought about the possibility that different source classes are being mixed in here when you're doing this host population analysis? If there are multiple formation channels for FRBs, then studying them together won't necessarily generate the right answer. What's the risk of that?
I see. Yeah, I guess with such a small sample size, it's kind of hard to split up and say, well, maybe we can draw lines between repeaters, non-repeaters, all that sort of stuff. I think even with kind of mixing them all together, we can start to get some sort of idea of, if there are any trends of, are they in places of elevated star formation, all of that sort of stuff. And then once the sample size grows substantially, then we can kind of split it up.
Once the sample size grows, it'll sort itself out as probably.
I think so, yeah. Yeah.
All right, we have 2 other questions. One from Casey Law. He says, great work. Tendulkar et al. Found that FRB 180916b was offset from its nearest star forming region. Can that analysis be done for your sample?
So I think that we sort of saw that too. I think you can see that a bit in the localization of like 180916. or not 18916, sorry, 1906-08. In that, like, the center of this localization is not quite on top of that star forming knot right there, but that knot is included within the localization itself. And sort of across the board, we didn't see the FRBs landing on the brightest regions in even the UV images, or that would show us these star forming regions in the host. So I think that we agree, but I think that we need deeper imaging for the UV to really probe that, to really see where are the brightest star forming regions, and really look at the offsets between the FRB localizations and those. Yeah.
And Jason points out that the 121102 is also slightly offset from the peak of star formation. Another question from Zorwar. Are there any hostless FRBs with HST?
I don't think so. I think we really wanted to focus on FRBs that had a very secure, like, host association.
So that's a source selection. Yeah. Okay. So maybe later on.
Yeah.
Yes. And finally, a question from Mohit. He says, awesome talk. How confident are we that the sources of these FRBs are not associated with globular clusters? Can we say anything about that?
I don't know. Yeah, I don't think I can really say anything about that right now.
Too early, probably. But we'll see. All right, well, thank you very much. This was a phenomenal talk. Thank you again. And we will keep going so far. And thank you, people, for keeping on time so far. Our next speaker is Wenbin Liu at Princeton University. And he's going to be talking about the implications of the M81 FRB in a globular cluster. Take it away. And I'll warn the 12-minute mark.
Thanks. So hi, everyone. So today I'm going to talk about this very interesting globular cluster hosting FRB, which came from these observations. I won't have time to go into the detail of the introduction. So hopefully people already know that there is this FRB repeater in a globular cluster, which is at offset distance projected distance of about 20 kiloparsecs away from M81, which is at 3.6 megaparsecs from us. So here's an outline of the talk. I'm going to talk about the implication, meaning the theoretical implication on the lifetime and energetics and formation pathway of the object, and the emission mechanism. If I have time, I'll go through the FRB population. So there's a very, very simple argument on the active lifetime of this source. Here's the argument. So the total number of neutron stars in the M81-like galaxy is about 10 to the 5. There's not much more than that in the galaxy. And in the most optimistic case, where you assume all neutron stars in globular clusters are capable of emitting FRBs in their lifetime of 10 giga-years in the past, here's the fraction of that 10 giga-years that is active. So that's the fraction of the total source that are active. And taking into account Poisson fluctuations, there's at least 0.1 such active sources at present day. And that gives you a very conservative lower limit on the active lifetime of the source. So you can immediately say that this source is not a typical galactic soft gamma ray repeater. It's much older than that. So the next thing is on the energetics. We know the isotropic luminosity. So this is the luminosity, not the luminosity of FRB, but you taking into account all the bursts that were detected within the exposure time, and then isotropic equivalent to that. And that you get something, it's a very small luminosity. It's not like a very, very bright source in terms of radial emission. And from that, and from the lifetime, and also one has to make assumption on the emission efficiency, one gets the energy budget of the system. So the system must have 10 to the 43 ergs or more in order to generate FRBs for such a long time, tau here. So here I'm taking a very, very conservative radial efficiency of 10 to minus 3 shown over here. For comparison, the galactic FRB had radio efficiency. This is over all emissions. So most of the energy is really emitted in the X-ray band for the galactic SGR, whereas I'm taking 10 to minus 3 as a very conservative limit, which gives the lower limit on the magnetic field strength. So it has to be 10 to the 13 Gauss or more. Another observational limit from the X-ray, from Chandra X-ray observation, limits the spin down luminosity of the system because of a non-detection of X-ray limits the spin down luminosity to be less than 10 to the 39. It's not the most young and powerful millisecond magnetar that is ruled out. And this also disfavors supergiant Pau's models as advocated by these authors. So putting in a PP dot diagram, here is what the constraints are. So this is the showing in purple is the X-ray upper limit. So the most rapidly spinning down objects are ruled out. And here's the age showing in brown. So the youngest things are ruled out. And here is the B field strength. We're saying so only in this region, which is consistent with some old-ish, some of the SGR, some of the magnetars are over here. I think the source is consistent with one of these kind of old-ish, but slightly lower magnetic field magnetars. And there is also an upper limit on the age of the system that is given by the magnetic field decay, given by the ambipolar diffusion. I won't have time to go into the detail how this is exactly calculated. You can go to this paper by Peter Goldreich and Reisenegger. So here's the ambipolar diffusion lifetime. After this time, basically the interior neutron star, the B fields in the neutron star core is dissipated. And here are some uncertain parameters. This is the length scale over which the variation of the B field occurs, which is normalized to about 1 kilometer in size. And here's the temperature. So you can see there's a strong dependence on the temperature of the neutron star core. So as the neutron star cools as a function of time, the ambipolar diffusion time becomes shorter and shorter. So roughly speaking, about 10 to the 5 years is about the time when the neutron star core cools enough such that there is no more interior magnetic energy. So that one can work that out, get the lifetime of the neutron star function as a function of the interior magnetic fields. You can see that given some uncertainty over here, the maximum lifetime if the FRBs are magnetic powered is about 1 million years. So the next thing I'm going to talk about is the formation pathway. How is such a neutron star formed in a globular cluster? This has also been talked about by Kyle Kramer. So there's a very simple argument. So it's the number density of such sources in the universe, which can be obtained because we know the nearest object of a given class, assuming homogeneous distribution in the universe. Here's the cumulative distribution of number density of such sources given the enclosed volume of the nearest object. Here's M81 FRB. For comparison, I'm also showing R3, which is one of the most active sources on the sky. This is at a much larger distance of 150 megaparsec. This one is about 4 megaparsecs. And so you can see that these sources are quite abundant in the universe. Roughly speaking, there's one per Milky Way-like galaxy. A curious fact that is the number density ratio of the two things. We also have the mean luminosity, time average luminosity ratio of this thing. And you find that the product of these two is comparable. It's just a fun fact. So in terms of formation pathway of the M81 FRB, here I'm showing, it's very simple. So you have the number density, which is constrained by observation. And we also have some constraint on the lifetime. So that constrains the formation, the birth rate. And that gives some hint about the formation pathway. Here's what's allowed by observation. Here's the lifetime. It's been between 10 to the 4 and 10 to the 6 years. I would say most likely it's 10 to the 5 years. So the birth rate of these objects are in this range. They're not near the core collapse rate. They're much less than the core collapse rate. And I found that this is consistent with one of the potential channels, which is the massive double white dwarf mergers, which has been advocated by Kyle Kramer et al., which has this rate. You can see that it's allowed over here. That's shown over here. And I would say some double neutron, a tiny fraction of the double neutron star is maybe slightly, maybe allowed, but it's taking into account this is in the globular cluster, I would say double neutron star merger is very unlikely. More likely it's a white dwarf mergers. So how does a massive white dwarf merger make neutron star? Here's the most recent picture. Goes like this. After the merger, if detonation is, if the system does not detonate, then you have viscous, the system undergoes viscous evolution and becomes a roughly spherical, inflated red giant, hundreds of solar radii. And there's a very large uncertainty on the mass loss of such a red giant. If the remaining mass is more than a 10 to the second mass, then you get a neutron star. If less, then you get a massive magnetized white dwarf. Here's the most recent work done by Josiah Schwab. You can imagine this is the mass at merger. This is the final mass. Of course, there's uncertainty on the mass loss history. This is one of the fiducial values, but it can vary by an order of magnitude up and down. So the final fate is really unknown. But you can see that it's possible that massive white dwarf mergers do make neutron stars. Let me gonna skip this. If I have time, I'll come back to this. This is related to the formation pathway of R3, which many of you may also be very interested. R3, the number density is tiny. So the birth rate must be very small, and the lifetime cannot be shorter than 10 years. So you can see that their formation rate is less than about 10 per gigawatt cube per year. So it's unclear what extremely rare type of stellar collapse made that. So going to this emission mechanism, so there is a near field and far away model as we discussed earlier. There are all these references shown over here if people are interested. So the key constraint comes from the variability time. This is done by Walid et al.'s observation. They found the variability time of one of the bursts from M81 FRB is shorter than their time resolution. So in the faraway model where you have an ejection from a neutron star or black hole going to very large distances R, and this ejection drives a forward shock into the ambient medium. So the duration of the FRB is given by the causal connection time. And it's very, very difficult to achieve variability time much shorter than the FRB duration. That is because the observer sees the entire cone of 1/gamma contribution, and that smeared away all very short variability time that may occur on a very tiny volume. So a way out of this variability time is you have propagation effects at much larger distances than where FRBs are generated. This is one of the nonlinear effects where the FRB pulse has a very high amplitude, and that can break into fragments in both the longitudinal direction and transverse direction. That can induce very short variability time. However, we have taken that model and looked into how such a short variability time can be generated. This is what that model can give. So here I'm showing the variability time in log space over here. Here's 1 microsecond, 1 millisecond, and longer. And here are the different constraints that we have. So in the best case scenario, the system, this scenario, the propagation scenario due to nonlinear propagation effects can give you variability time about 200 nanoseconds, which is much longer than what's observed or what's inferred to be less than that. So we think faraway models are disfavored by the observations. So I think I still have time to talk about FRB population, which is so nice. So here I'm showing the FRB rate. Here is the cumulative rate. So a rate per unit volume, per unit time, greater than some FRB energy. So the FRB energy is given by the fluence multiplied by 4 pi distance squared. And showing here are a couple of constraints. Here's the ASCAP. So ASCAP had their fly-eye survey, which was only sensitive to bursts brighter than 10 to the 31 erg per hertz. So these are where ASCAP is very sensitive. And on the high energy side, ASCAP, this small number statistic, then the error becomes large. So ASCAP did not have much constraint on the lower energy end, but you can extrapolate backwards. And you can show that the extrapolation actually is consistent with the measurement from the M81 FRB as well as the Galactic FRB shown over here. And the whole thing, the whole FRB population is consistent with a single power law, with the power index of the cumulative index of -1. Here is what if you draw a line over here, that's what this line is.
3 minutes, Wenbin.
Thanks. I have one last slide. Yeah, so another thing I want to introduce, the final thing I want to introduce is the luminosity density. So how much energy is emitted by all FRB sources per unit volume, per unit time. Here is the per unit time shown here, you may not be. So the answer is about 1,000 solar luminosity per gigaparsec cube. So FRBs are not great at emitting energy, at injecting energy into the universe. So here are, what you get is, because we know the number density of these sources and we know the mean luminosity of these sources, here's what you get luminosity density from these three classes. This is R3, this is a M81 FRB, and this is a Galactic FRB. You can see that roughly speaking, all these classes of sources, they actually form kind of a uniform injection, kind of a uniform distribution, despite their mean luminosities being very different. And another conclusion you can draw is that because this class of sources come from old stellar population, and you find that old stellar population contributes at least a few % of the total FRB luminosity density. I have the summary slide. So here's the summary slide. We found that this M81 FRB source is consistent with the old neutron star, basically, but it has to be quite magnetized. It's a slowly spinning, and it's most likely formed from double white dwarf mergers with total mass exceeding the Chandrasekhar mass. And the FRB emission mechanism is most likely from within the magnetosphere instead of far away. And we think old stellar population contributes at least a few % of the FRB rate. So people should target those, old stellar population like galaxy cluster and big galaxies. And here are the other things. Thanks so much.
Well, thank you. That's very nice. We do have time for a couple of questions. There's a comment from Brian Metzger in the chat where he says, as he pointed out in his talk, the beaming is not 1/gamma if the upstream is highly magnetized. It is smaller by a factor of 1/sigma, where sigma is the upstream magnetization, which can be very large. Mm-hmm. And
yeah, to answer that question, because my gamma is not really the gamma of the pulse of the shocked gas, it's the gamma of the shock front. So that has already been taken into account.
Yes.
Thanks.
Yes, and as Benyamini also points out, that the efficiency is reduced by roughly the same factor. Mm-hmm. Question from Brian Gensler. The lower limit on the magnetization of M81R comes from assuming a source with the volume of a neutron star? Are larger sources with less magnetization possible?
Yes, indeed. It's assuming a neutron star, volume of a neutron star. So if it were a white dwarf, which I consider as unlikely. So basically right now we're assuming it's a neutron star from the beginning. If it is a white dwarf, then of course from the energetics, you require a much less magnetized object. Thanks.
Yeah. One more from Jason. In Nimmo et al., we showed that there are occasionally 60 nanosecond isolated shots of emission. But we also showed that some bursts don't resolve down to short duration shots. There's a range of timescales spanning over a factor of 1,000. How does that fit into the picture?
Yes, thanks so much. Exactly. So this is, here I'm not showing, I shouldn't say, sorry, this is a confusing part. I shouldn't say this is a variability time. I should say the shortest variability time, because that's what's the most constraining. Of course, any source that is capable of generating very short variability time may also be able to generate, a slow variability given in an envelope of the light curve. So this is specifically the shortest variability time. So there's no contradiction. The longer variability time, there's no contradiction with either of the models.
Mm-hmm. Yeah. One last one from Bing Zhang. The binary white dwarf mergers make neutron stars that are not very special. So what is the fraction of those mergers that will make neutron stars that satisfy your PP dot constraints?
Mm-hmm. That's a very nice question. So these ones could be very special because the white dwarf merger injects a huge amount of magnetic energy into the system, which could be, in naive way, could be 10 to the 50 ergs of magnetic energy, which is a binding energy of a white dwarf. And that some mass loss may get lost, some of that magnetization may get lost, but these ones should be very highly magnetized. One observational fact is that the ZTF team has observed one of the very highly massive. So the mass of this white dwarf observed by this team is right here. And that magnetization is capable of, if it indeed collapsed to a neutron star, is capable of generating 10 to the 13 Gauss. So no problem. So I would say most of these mergers, if a neutron star is formed, should be capable of generating, M81 FRB-like emission.
All right. Okay, well, thank you, Wenbin. Thanks again for a very nice talk. There is a lot of stuff happening in the chat, and I will recommend taking that to a thread on Slack so that it can be preserved, because the chat disappears once this Zoom session ends. So please do put that in the chat.
Thanks.
All right. Moving along, our next speaker is going to be Wen-fai Fong from Northwestern University, and she is going to talk about the dusty star-forming host and Arcsecond localization of the remarkable repeating FRB 2020-1124A. So Wen-fai.
Great, thanks. Can you see the slide okay?
Yes, and I'll give you a 3-minute warning.
Okay, thank you so much. So as Shami said, my name is Wen-fai Fong. I'm at Northwestern University, and I'm new to the field of FRBs, but coming from the world of gamma ray bursts, this is extremely exciting to be a part of, and I see a lot of similarities with that field, particularly in the early days, but a lot of differences too that are very exciting. And it's just been such an interesting conference so far. I've learned a lot. So today I'll talk about the remarkable repeating fast radio burst 2020-1124A and its environment. I know many of you are very familiar with this burst, having been involved in campaigns around the world to localize and catch this burst in action. And this particular paper that we submitted a couple of like 6 weeks ago was in collaboration with a large group, in particular the Fast and Fortunate FRB follow-up collaboration and CRAFT. And I just wanted to highlight the numerous PhD students and postdocs also involved in this effort. As one of the things I love about FRBs too, is I've noticed how these young students and postdocs get elevated platforms when it comes to scientific discovery, which is excellent. I also want to note that there are 2 other great papers, at least, maybe I missed one in the last 24 hours, but that came out on the archive with some focus on the host galaxy. So I urge you also to check out those really nice papers, and I'll highlight some relevant results here too. Okay, so I know we're kind of mid-session, so I want to do a little bit of an icebreaker to wake you up, but really I promise this comparison between this fast radio burst and my nephew is relevant. So this is a picture of my nephew, if you haven't guessed. For one, both were born or discovered on November 24th, 2020. So this is a really special and exciting fast radio burst for me to study. I didn't actually get to meet him until just last week when he was 8 months old. And I was also happy to learn that both this fast radio burst and that my nephew are prone to outbursts of activity with absolutely no warning. I know that the fast radio burst has undergone a period of silence since late May. That's not the same for my nephew, so that's one difference. And both, this is kind of a stretch, but both have fondness for color, as you can see in this picture of him, and fondness for the full EM spectrum, as you'll see throughout the talk. All right, so on to science. So this is a timeline of FRB 2011-24A. I just wanted to kind of put everything into context. I know we've had several talks on this burst, but this is just to kind of give a full view, because this is the first talk on it in a little bit, a couple of days. So the CHIME FRB collaboration discovered this on November 24th of last year. About 4 months later, they announced a period of high activity, and they were absolutely right. So this FRB kind of went like gangbusters. As part of, in conjunction with the ASCAP CRAFT collaboration, we detected the FRB and follow-up searches and provided an arcsecond localization, and thus a host identification that landed right on a host galaxy. Meanwhile, FAST also was detecting 100 FRBs at the same time, which is amazing and crazy at the same time. The UGMRT was also performing follow-up a few days later, and they detected FRBs as well as persistent radio emission, which was interesting. We obtained an MMT spectrum of the host galaxy just a few days later to nail the redshift down to a fairly local redshift of 0.098. Meanwhile, the VLA real fast team swept into action and localized the FRB. And then further results from the VLA also confirmed the presence of persistent radio emission at gigahertz frequencies. And then the EVN chimed in, and no pun intended, chimed in, and also found the FRB pinpointed to milliarcsecond precision, which again solidified the host galaxy association and the persistent emission. They found they did not find evidence of persistent radio emission in their imaging, and so thereby saying that this was resolved out and probably not compact, so placing a lower limit on the size scale of a couple of hundred parsecs. Meanwhile, Stockert, which I hear was a breakthrough for this facility, detected an extremely bright FRB in between this action, which was momentous for them. And there was also further follow-up by Unsala and the Allen Telescope Array. And meanwhile, CHIME was detecting this thing throughout the entire period. There was a break in between, but it was covered by many other radio facilities. And I think the last activity, according to the website, was late May. So just to put this into context, this is an extraordinary global and rapid follow-up effort. I think this is a great test of independent localizations from many different teams. This also, I think, highlights the importance of really rapid communication, which I'm sure you all are aware as you all participated in that. And that really helped us try to identify the host extremely quickly. The persistent radio emission we found was not, the community found, was not a true compact persistent radio source. There's been greater than 200 bursts reported to date. I'm sure there's many more lurking in data sets, and campaigns are still ongoing. So this is a really extraordinary, remarkable event to study. Okay, so I'll focus a bit on the ASCAP localization and observations of this source. So these are the 3 bursts that were used for localization. There were actually 11 ASCAP bursts detected in total. 3 are available for with downloaded voltages, where we can actually use the localization information. And we detected it in both the mid band and the high band at a variety of fluences. And the DM was consistent with other DMs reported around 412 to 414. And the papers are in the works for the details of the remaining 8 bursts that we don't present here. In terms of localization, I just want to kind of give you a lay of the land, and I'm going to split this on the left-hand side into the FRB localizations, on the right-hand side into the host or radio emission localizations, because it's too much to put on one plot. So this is archival Pan-STARRS imaging. It provides a pretty nice view of the host, and the host center is marked with the yellow X. Here are the ASCAP localizations. So each of the purple dashed lines represent 1 sigma localization of an ASCAP burst, and then the joint position, performing a joint probability map, we get 1 and 2 sigma contours in pink. And as I said, EVN also nailed the position of this burst, and we can see that we're fully consistent with their pinpointed location. So going on the right, this is the same exact field of view, but there were I just wanted to point out different positions. So now this is really focusing on the host galaxy. And so overlaid are the VLA and UGMRT persistent radio emission, the extended persistent radio emission localizations. You can see they're fairly consistent with the host galaxy center and also marginally consistent with the FRB localization. And just a couple of nights ago, there was a detection of the paper that said a detection of the VLA host at 22 gigahertz, and just trying to pull the coordinates from that paper and put it on, this is where they fall. You can see it's more co-located with the FRB localization, but maybe marginally consistent with the host center. So for sure, it seems like this host radio emission is kind of bobbling around. Not in reality, but just as we improve our localization. Okay, so this is our MMT spectrum where we were able to obtain the redshift, and this placed the host at a redshift of 0.0979 plus or minus 0.0001. And you can see the detection of several emission lines. Curiously, our spectrum was so high signal that we were actually able to pinpoint some mysterious unidentified lines initially at this redshift. But I always say spectroscopy is truth. It really can tell us way more than imaging can. And we actually associate this to a background galaxy at a half arcsecond offset that really happens to be there by chance. And we can rule out this redshift to fairly high confidence based on the burst dispersion measure. So using the emission lines, we can actually place this on a BPT diagram to understand where it is with respect to AGN versus classic star-forming galaxies. This is from Shivani's paper, and she showed this plot, but I'll just show it again, that it really is identified as a classic star-forming galaxy with a moderate star formation rate of 2.1 solar masses per year from H alpha. So we undertake a full modeling of the host galaxy with Prospector. This is the one slide that I'll kind of geek out a little bit on modeling, stellar population modeling techniques, because I think I just want to highlight a couple of things that we're doing differently from the current transient community. And so this is a 12 filter plus spectrum fit with Prospector, and we undertake nested sampling with Dynasty versus MCMC. So that actually has the advantage of not being as sensitive to your priors and not falling into solutions that may or may not be real. We also perform joint fitting of the photometry and spectroscopy to use the full power of the data set, as there's a lot of information encoded in the spectrum itself. We employ non-parametric star formation histories, meaning we're agnostic essentially to how the stars were being formed over time. And that's really important in terms of understanding other stellar population properties correctly. And then we also use mass weighted ages. So I could go on forever about ages, but they're a really difficult thing to pinpoint. But many of the ages you'll see in the literature in general are based on simple stellar populations or light weighted ages. And those are generally biased toward where the light is from more massive stars and will be biased toward younger ages. So the mass weighted ages that you'll see coming from our works are generally older than those light weighted ages, but are a bit more reliable in terms of understanding when a progenitor could have formed and that kind of thing. And just to show you how well our model does with the spectroscopic fit, this is just a zoomed in version of the Prospector model with our MMT spectrum, and you can see almost every believable bump and wiggle we are able to fit very well.
3 minutes.
What?
3 minutes.
Okay, thank you. All right, so this is the upshot. So this is the stellar population properties. In other words, it's a fairly normal star-forming galaxy, moderately dusty. Some things of note, it's of subsolar metallicity, which is kind of interesting. And there might be a hot dust component contributing to the mid-infrared luminosity. Another thing that we're able to reconstruct is the star formation history. It's remarkably constant over its 10 gigayear history. And so just in case you're not used to looking at plots versus look back time, T look back of 0 is the time at the FRB redshift. And then you go back in time as you go leftward on the x-axis. And so this is just a fairly constant star formation history. It drops in the past 30 million years or so, but there's no real evidence of starburst activity or anything that could be potentially associated with such an active repeating FRB. And just as an example, this is just purely for context, nothing to do with FRBs, but the host galaxy of GW 72817, which was a binary neutron star merger, had a rapidly declining star formation history, just to give you context for the diversity of star formation histories that exist out there. And of course, this is a very old host with a long delay time. So this is just for contrast. We can also construct the mass buildup history to understand over the course of the galaxy's lifetime when mass was built up. So this is basically saying if the progenitor purely traced stellar mass in the host galaxy, it's likely greater than a few gigayears old. Of course, we have heard that from previous talks, probably that there's more to repeating FRBs than just stellar mass. For the broadband view, we can confirm that the continuum radio emission is from star formation. So this is from Vikram Ravi's paper, and I know there's other contributions from ATELS in this, where it showed that this basically follows a power law or a broken power law. Putting the entire broadband SED together, we see that the radio emission agrees very well with a nu to the minus 0.75 classic star formation power law and connects really well with the rest of the available data. And we can fairly solidly rule out a strong AGN contribution. So this is one of the first repeating FRBs with detected host star formation in the radio bands. I think M81 might be the only other one that has the advantage of being very close by. We can also set some sort of size scale based on the available measurements in the literature. And this implies a size scale of less than the galaxy. And so at first we thought this might be due to some circumnuclear star formation activity. But recent work just posted a couple of days in the archive suggests that maybe at least at 22 gigahertz, this potential radio emission or star formation activity might be more co-located with the FRB site than we expect. And so that's very interesting and clearly highly sensitive, high resolution sensitive imaging in the radio and optical is needed to really delineate the true substructure and its relation to the FRB. And just one last slide. So I just want to end with just a kind of thought. If is a compact PRS like those of 121102, and we just heard about 1905-20 possible. And so I grabbed all the available data. And so this is just to put into context where the existing limits on such a PRS for 2011-24A sit with respect to the known PRSs. And so this PRS would need to be greater than 20 times less luminous than known compact PRSs. But I think it's worth trying to look at models and understand that they're and so under certain models, PRS luminosities can in fact be time variable and span orders of magnitude. And so I think this is kind of an interesting possibility. Okay, I had a few more things, but I will just end with a couple of conclusions and leave it up and just advertising the VLT large program coming up that we've heard about. All right, happy to take questions.
Phenomenal talk, and oh my, that is an acronym you've got there. That is phenomenal. We're going to squeeze in a couple of quick questions. One from Emily Petrov for Wen-fai. Without the spectroscopy, would it have been possible to find out that there was an overlaid background galaxy? And what is the probability of such an overlay? And while it maybe isn't a possible host for this FRB, should we be worrying about this for other FRBs?
No, great question. We did a very quick calculation. The probability of a random chance galaxy in your background is fairly low, but it also depends on the luminosity of that galaxy. With available data with archival imaging like this that I'm showing, it would have been it's impossible to see anything in a half arcsecond offset in the background. But with HST, it should be possible to maybe see a contribution. But again, without knowing more about the luminosity of that source, it's going to be tough. So yeah, spectroscopy is truth. I don't think we should be worried about it necessarily, though, given that if for future FRBs, given that it is fairly low probability.
Okay. And another one from Brian Gensler. What can we say about the Hubble type of this host and the location of the FRB with respect to the main features, the nucleus, the spiral arms, and so on?
Yeah, not much now. I think our best indication comes from that K-band observation the 22 gigahertz observation I was showing. Carol, I'll show it again. But basically, our current archival data is not sufficient to place any constraints in the morphology of the host or any meaningful constraints. Certainly HST could do a much better job. And the thing kind of went behind the sun right after it was discovered or entered a period of high activity, but we're anxiously waiting for it to come back to characterize it in the optical.
Right. And then I'm going to put this in here as well for you. Mohit asked on the Slack, Mohit Bhardwaj asked, for Wenbin Liu, but perhaps also for you, how confident are we that a type 1a supernova is a good proxy for AIC?
Oh, that would maybe be more of a Wenbin question.
Okay, so maybe not for you then.
Yeah.
Okay, we'll take that up in the Slack. Okay, well, thank you again very much. This was a great talk and phenomenal results. It's just really, really nice to see this kind of stuff. So thank you, Wen-fai. Our next speaker is Fayin Wang from Nanjing University, and this is going to be a recorded talk about DM host and DM IgM of FRBs derived from the TNG simulation and cosmological applications. So take it away.
Hello everyone, my talk title is DM host and DM IgM derived from the TNG simulation and the cosmological applications. This is a quick outline of my talk. First, I will introduce what are FRBs. Then I will show the results of DM host and the DM IgM derived from IllustrisTNG simulation. Then the cosmological applications are discussed. Last, I will give a summary. FRBs are transient high luminous events with a few millisecond time scale. The first FRB was discovered in 2007. They were confirmed with a large sample after 2013. The most striking feature of FRB is the frequency-dependent arrival time, which is shown in the figure. According to the dispersion relation, the time delay is related to the dispersion measure, as shown in this equation. The DM is defined as the column density of free electrons along the line of sight. The dispersion measure of IgM combined with redshift is important for the cosmological applications of FRBs, such as missing baryon problem, dark energy, Einstein equation principle, large-scale structure, cosmic distance, Hubble parameter, dark matter, and Hubble constant. However, the DM IgM cannot be obtained directly from observations. The variance of DM IgM is large. How to model DM IgM is crucial. According to the origin, the observed DM can be separated into different parts. For example, the host galaxy, the IgM, the halo of our Milky Way, the ISM of Milky Way. For the DM Milky Way and the DM halo, we have models to describe them. However, from observations, DM IgM and DM host are correlated. People may ask, what the probability distributions for DM host and DM IgM? In order to study this problem, we use the IllustrisTNG cosmological simulation. This simulation is a state-of-the-art cosmological simulations, which give detailed distributions of particles, dark matter, star formation rate, metallicity, and elect. 3 physical simulation boxes are employed. For example, 15, 100, 300 megaparsec side lengths. The large simulation box can be used to study the large-scale structure of the universe. For DM IgM, we use the TNG 300, while the small simulation box can provide a better resolution of galaxy, which is important for the structure of galaxies. For DM host, we use TNG 100. The method to derive DM host. First, according to the observational properties of FRB host galaxies, such as stellar mass and star formation rates, we select galaxies that are similar to the host galaxies or localized FRBs. For repeating FRBs, these two localized repeating FRBs have different host galaxy properties, such as stellar mass and star formation rate, so we study them separately. For non-repeating FRBs, we treat them as a whole. The location of FRB in the galaxy. For repeating FRBs, considering the magnetic origin of FRBs, they are mainly produced by core collapse. Therefore, we assume that the probability of FRBs occurring in a galaxy is proportional to the star formation rate. For non-repeating FRBs, some have very large offsets. Assume that FRBs are produced by the mergers of binary neutron stars. We have calculated the locations of FRBs using binary stellar evolution code. This can well explain the short GRB offset distribution, also can produce the large offset of FRBs. The electron number density NE is calculated from this equation. The values of the parameters are all given by the simulation. Then we can obtain the DM host by summing the NE times dot L along a given line of sight. In the calculations, we select 1,000 galaxies similar to the observed galaxies, 500 FRBs in each galaxy, and each FRB has 10 random directions, so there are totally 5 million DM hosts and each redshift from 0.1 to 1.5. In the figure, we show the DM host distributions for the two repeating FRBs. The histogram shows the DM distributions derived from TNG simulation. The red lines show the log normal function fits. The shaded region gives the observational constraints on the observed DM host. The DM host of non-repeating FRBs are shown in this figure. The shaded region is the observational constraint on the DM host. We can see the distribution of DM host can be well fitted by log normal distributions. The best fitting parameter of log normal functions are shown in this table. We also find that the DM host increase with redshift. The evolution of the median value of the DM host can be fitted using this equation, which is proportional to 1 plus c. The reason is that the common free electron density is almost constant from redshift 0.1 to 1.5, as shown in the bottom figure. So the physical value of the electron density increases with redshift because we should convert the common density to the physical density. We also test the dependence of our results on the properties of galaxy. We select galaxy with a narrow range of stellar mass and star formation rate. For the wide range, as we have done before, the stellar mass is between 1 to 50 times 10 to 7 solar masses. The star formation rate for the two cases is almost the same. For the narrow range, we select the stellar mass in the range from 4 to 7 times 10 to 7 solar masses. In the figure, we show the distributions of the host DM for the two ranges. It's clear that the two histograms are constant with each other. Below, we show the DM IgM derived from TNG 300 simulation. Previous theoretical studies treated DM IgM with a homogeneous universe. The average value of DM IgM is widely used as this equation. The effect of IgM in homogeneity will cause fluctuations of DM IgM. DM IgM have been derived from different cosmological simulations in low redshift universe. IllustrisTNG has two advantages compared to previous simulations. First, it can provide the electron density directly instead of converting the dark matter density to baryonic matter density. Second, The IllustrisTNG covers a wide range of redshift up to redshift 9. Show the method to derive DMIGM. First, the line of sight is chosen to be parallel to the x-axis. Then we construct 5,000 square pipes of side length 200 moving kpc in each snapshot. The 5,000 pipes are chosen from different locations in 24 snapshots randomly. Then divide the pipe into 10,000 bins. The distance between each bin are calculated. We take the average of electron density of 10,000 bins and put it into the right equation to obtain dmdt. 10 million dm-IGM relations are built by randomly select dm divided by dt from redshift 0.1 to 9, as shown in the dotted lines. Dotted lines are fixed using a Gaussian function with a long tail. The long tail is caused by the FRBs goes through high density region in the IGM. From the last panel, we can see at redshift larger than 7, the distributions are overlapped, indicating that our universe do not realize at high redshift. The DMIGM can be well fitted by a Gaussian function with a long tail. The best fitting parameters are shown in this table. In the left figure, we show the DMIGM redshift relation. The blue line is our result from TNG simulations. The blue shaded region is the 95% confined region. We also compare our result with the previous estimations. We can see for most of them, they are constant. In the right panel, we show the localized FRBs. And redshift 1, the value of DMIGM is 900 plus 700 minus 300 pc per cubic centimeter. The uncertainty is up to 19% and redshift 1. So we discuss the cosmological applications. The first is the cosmic reionization history. In the figure, the green and yellow lines are constraints on reionization from CMB observed by Planck. The red lines is the best reionization fit for IGM-DM derived from TNG 300, which is consistent with the reionization model used in the TNG simulation. The reionization redshift is about 6. This also supports that the derived DMIGM is robust. The second cosmological applications is the CMB optical depth. The optical depth back to redshift D can be written as the integral of electron density times the Thomson cross-section along proper length, which is shown in this equation. Our result gives this the optical depth is 0.037, shown as the blue region in the left figure. The yellow region shows the results by Planck observations. So our results are consistent with the Planck observation. The third application is to measure Hubble constant. The average value of DMIGM is shown in this equation. From above analysis, we obtain the probability distributions of DM host and the DMIGM. The likelihood function of Hubble constant can be derived with this equation. From the 14 localized FRBs, we can measure the Hubble constant, which is shown as the third line in this figure. In this figure, we also show the Hubble constant measured by CMB type 1 supernova, and gravitational waves. We can see our measurements with a precision about 8% is consistent with the value derived by CMB. For more details, see Qingwu's talk. Summary. The distributions of DM host can be well described by a log normal function, and the median value of DM host increases with received. DMU-RGM can be well fitted by a quartz Gaussian function with a long tail. They can be used to measure pseudo-received or non-localized FRBs. For cosmological purposes, using the probability distributions of DM host and DMU-RGM is important. That's all. Thank you. Hello, everyone.
Well, thank you for that. Unfortunately, we don't have Fayin Wang here in the discussion session, so I'll take the couple of questions that we have put them on Slack, and hopefully he will answer them later on when they get to it, when he gets to it. Okay, so I think given that, and we're doing decently well on time, we will move right along to the last talk in this session. And this one is by Liam Connor at Caltech, and he's talking about mega Jansky galactic bursts and a mega source survey. So Liam, take it away.
All right.
I'll give you the 12-minute mark warning with 3 minutes left warning.
Sorry, I've just got to move something. Okay, great. So yeah, today's talk is going to be about searching for FRBs on large field of view surveys. So I'm going to start by talking about GREX, searching for more mega Jansky bursts like the one that we detected from SGR 1935 last year. And then I'll imagine what it might look like if we try to search a steradian field of view, like what GREX will have, but with approximately the sensitivity of GPT or even better. So we all remember the excitement last year in April when a magnetar in our own galaxy, SGR 1935 plus 21, emitted this extremely bright, very energetic burst, which was detected both by STARE-2, which you can see in the bottom left here, and by CHIME FRB in the side lobes. And this was hugely informative. Of course, it created this dramatic link between the extragalactic FRBs that we've been studying for the past 10 years and magnetars in our own galaxy. So it's natural to try to create another experiment, maybe with more sensitivity, more sky coverage, more exposure to the galactic plane, the southern sky, to search for more of these things, kind of acting as a radio all sky monitor, analogous to how in the X-ray there are wide and shallow X-ray surveys that really complement the smaller field of view, but more sensitive X-ray telescopes. So the point of GREX, the Galactic Radio Explorer, sort of a rebranded STARE-3, is to find more of these galactic FRBs to search for supergiant pulses from pulsars in the Milky Way. We're going to be running a blind, roughly 10 microsecond search, which I can describe a little bit more in a couple of slides. Fast solar physics, and then of course, unknown unknowns when you search this kind of new parameter space with an enormous field of view. So this is the basic idea. Each GREX cluster will be made up of 3 antennas. So there's no dish, it's just antennas pointed at the sky, like with STARE-2. And then we'll deploy these 3 antenna clusters around the world. And within those clusters, the antennas are separated by roughly a horizon scale so as to discriminate RFI. And by placing them around the world, we might need 8 or so of these clusters, and you can build up exposure to the full sky such that you have continuous 4 pi steradian coverage. So this is going to be about 5 times larger frequency band than STARE-2. It's going to be an ultra wideband feed, so between 0.7 and 2 gigahertz. We're going to capitalize on the very low noise electronics that have been developed for the DSA, which Vikram talked about yesterday. And so we'll be sensitive to roughly 100 kilojansky bursts with a millisecond duration, maybe a little bit lower. And for the top quarter of our band, we're going to be searching down to roughly 10 microseconds. So as I mentioned, we're using these ultra low noise electronics developed primarily by Sandy Weinreb here at Caltech, and now with the help of his graduate student, Kieran Shaila. And these have really great performance. They're roughly 8 or 9 Kelvin over most of the band. And we're also going to be using the ultra wideband receivers developed by Jonas Flyger at Onsala in Sweden. And he's created these for DSA 2000. So again, this is really piggybacking on some really low noise and high performance instrumentation that's been built for these two projects, DSA 110, which has about half of its antennas now, and DSA 2000, which is still in the design phase. Okay, so we talked in last week's discussion session about the value of searching for the high time resolution data, but just how difficult it was. So Kendrick pointed out that you kind of get hit twice with this n-squared effect, where if you want to increase your sampling time by, for example, a factor of 10, you'll probably become dominated by DM smearing, and therefore you have to have 10 times more frequency channels, and so you might have 100 times more data to deal with. So one way to get around this is just to search at higher frequencies. DM smearing is, of course, much worse at lower frequencies. So our plan is to do a sort of customized channelization scheme in firmware, probably designed and built by Jack Hickish, where the top quarter of our band will have the same number of channels as the bottom 3 quarters. And because smearing is significantly less detrimental up there, the smearing curve is a lot better in the top quarter than in the bottom 3 quarters, as you can see from these curves, where I plotted the smearing timescale in microseconds as a function of dispersion measure. So you can see for the gray curve, this is where we expect to do our search for supergiant pulses, either from pulsars that we don't know emit supergiant pulses, or from pulsars whose regular radio emission is not pointed towards us. So discovering new pulsars in this manner. And you can see we're still in the sort of 10 to 15 microsecond regime at 100 or a few hundred DM units. So similar to SGR 1935. And now, because we're going to be moving into the southern hemisphere, we're going to get a lot more exposure to the galactic plane and therefore the magnetars that roughly trace star formation. So here I'm just plotting the magnetar fraction that's in your beam, that's in one of the G-Rex clusters beam at a given hour angle on the top and a given UTC on the bottom for 4 different locations. So in dark blue is Western Australia, and then GMRT in India, OVRO in the Netherlands. And you can see when you're in Western Australia, you really do have a lot more access to the galaxy's magnetars. So you can do some fairly simple modeling. And you can say, well, given we've got 5 times the bandwidth with G-Rex over stair 2, given we have about 3 times lower system temperature, and we've got a lot more sky coverage, including more exposure to the galactic plane, you can estimate, even just based on the one detection, how many of these galactic FRBs we might expect to see per year. And with these wide Poissonian narrow bars, you get maybe 2 to 50 events. So even if stair 2 and CHIME were really lucky in detecting this one event, and it's super rare, you should still expect G-Rex to find a couple of these each year. Okay, so let me now switch gears and continue talking about a large field of view survey, but imagine populating the G-Rex field of view with coherently formed beams and building up sensitivity that's a little bit better than CHIME's. So Vikram mentioned this yesterday, but if you look at all these really impressive telescopes that have done a lot of really exciting FRB science, you'll notice none of them was actually built to find or study fast radio bursts. So CHIME has done amazing things in the FRB field, and it was designed for cosmology. ASCAP was designed long before craft existed, aperitif to arts, and so on and so on. The one exception being DSA 110. But at this point, nobody's ever explicitly designed a survey whose goal is to maximize the number of FRBs per unit time, per unit dollar. So if you imagine a survey maybe starting construction in a few years, whose goal was just to find as many FRBs as possible, designing a sort of megasource survey that could find of order 10 to the 6 fast radio bursts, how would you do it? So one way to do this is to start with CHIME. CHIME sees about 1,000 FRBs per year. It's got an SCFD of roughly 50 Janskys and a field of view of 200 square degrees. These are my numbers, by the way, so they could be off by tens of percents. So one way to get 1 million FRBs is to have 100 chimes observing for a decade, right? You would move them, you'd have 100 chimes all around the world pointing at different places on the sky, roughly 20,000 square degrees, approximately a hemisphere of exposure, and you would have 100K FRBs per year. Another thing you could do is you could make chime longer and skinnier. So rather than having a 20-meter cylinder, it would be, say, 4 or 5 meters in the east-west direction. So now each cylinder has a field of view of about 1,000 square degrees. And then it would have to be longer in proportion, and maybe just for good measure, you would double the collecting area such that the SCFD was 25 Janskys. Again, with 8 long skinny chimes, we're at 100K per year. Another thing you can do, really leaning into the field of view thing, would be to do away with dishes altogether. And you would end up with something like what we see here, dense aperture arrays. So these already exist. You know, Embrace was the first one, I think. Embrace is over 10 years old. It was developed in the Netherlands at Astron. And this is a dense aperture array with 5,000 Vivaldi feeds packed together very, very tightly. It observes at 1 gigahertz. On the top, you see an artist's impression of an aperture array proposed for the SK core. An issue with Embrace is that, first of all, at 1 gigahertz, you don't have much collecting area. You only have lambda squared collecting area per radiometer. So that's only about 0.09 square meters per antenna in that case. Another thing is Embrace does hierarchical analog beamforming, so you don't ever actually have access to the full field of view. But you could imagine stripping those electronics and doing it all digitally over the full field of view. For an FRB survey, you probably want to be at lower frequencies so that you have more lambda squared power, more collecting area. So just to run through the numbers, how you would do this, remember the rate of detection for any survey is going to be the field of view times the number of sources within that field of view greater than some minimum brightness. So field of view times the either flux density or signal to noise threshold raised to the source counts power law index, which I'm assuming are Euclidean here, and I think that's actually a fairly safe assumption. Okay, so if we're observing between 400 and 500 megahertz, that's about half a square meter per antenna. And it turns out you need about 14,000 antennas to match chime's 6,400 square meters of collecting area. So suppose we have the same field of view as GREX, 20 to 30 times chime's field of view. So between 1 and 1.5 steradians approximately. You can plug in the numbers and you find that to get 100,000 detections per year, this would be about 50,000 antennas. And I'm assuming, by the way, that we can cut in half the system temperature compared to chime with improved ambient temperature electronics. So just to emphasize that I'm not trivializing this pretty incredible task, this is a grid of 220 by 220 antennas for 50,000 in total. And for each of these antennas, you need to amplify and digitize and channelize and send all of that data to a beamformer where you're going to create 50,000 beams. And then, of course, you have to search in real time 50,000 beams, excise RFI, all that stuff. So this is a massive task. And if
3 minutes.
Thanks. And if we use sort of current day technology for the front end and the digital back end, channelization and digitizing and such, we could end up spending over $1,000 per antenna, which would make this whole thing prohibitively expensive, because then you would end up with just sampling the thing at $50 or $100 million. So if you could get the cost per antenna down to order $100 for, again, the LNAs, the ADCs, and the channelization, then the budget is starting to look at least a little bit feasible. One way to do this, and by the way, I'm not an expert on this, but I understand it's starting to happen, is that you could put the LNA, the ADC, and the channelizer all in the same card. So if you could cheaply manufacture these very specialized ASICs that do all of those things, and then you just pump the channelized voltage data to an FFT beamformer, then you might be okay. By the way, if you put these antennas on a regular grid, then you can FFT beamform, which is n log n and not n squared. And searching 50,000 beams, of course, is pretty daunting, but it really is only an order of magnitude more beams than what we search currently in real time at Aperitif on 2016 GPUs. And actually, this would probably be done with lower time resolution than what's done at Aperitif. It's also worth noting that if you frame it like this, the total number of sources as this integral of the rate over time and over the relevant regions of parameter space, R of lambda, so where lambda can be dm, width, frequency, whatever. Before CHIME, actually before the first catalog was released, we really didn't know much about R of lambda. And now that we have this first catalog and we're going to have thousands of FRBs from CHIME, we really understand this distribution, which means for any upcoming survey, you can really tune your search, tune the regions of parameter space that you're searching to maximize the number of detections, and you might be able to get a factor of 2 out of that, which means you could decrease the number of antennas. Okay, natural question before I wrap up is, do we actually need 1 million FRBs? At what point do we start running into diminishing returns? And I think the answer is, if we don't need 1 million, then we at least need a lot more than we currently have. And we need them in a large field of view, or at least with the same pointing for things like gravitational lensing. So it's worth noting that gravitational lensing by a massive galaxy, which could be very exciting for lots of reasons that I would encourage you to tune into Wei-Li's talk later today. It's a rare event, and it also leads to delays, time delays from the lensing event that are days to months long, which means if you're not always pointed at the same patch of the sky, you're probably going to miss the lensed copies of the FRB. And so if the optical depth out to redshift 1/2, as shown here, is maybe 5 times 10 to the minus 4 or 10 to the minus 3 at most, you really need huge numbers of FRBs, and you need an enormous field of view, or to always be pointed at a celestial pole to actually see anything. And I think that's true. I think that's probably true for lots of the other really ambitious cosmological applications of FRB. I suspect that to do any EOR stuff, you need a huge number to map out large-scale structure, do the CGM, IGM, all these things. Having a few thousand per year is probably not enough. Okay, so let me just summarize by saying GREX is going to be this very shallow but all sky monitor, which could find an order of magnitude more of the FRB-like bursts that STARE-2 found. The first one will probably be deployed in the Smoky Valley in Utah. And then finally, very large N and very small d, taking that to its logical conclusion, could produce pretty enormous detection rates for fast radio bursts. And if we start thinking about how we would actually do this technologically, there could be huge returns. So I'll leave it at that, and I would happily take questions.
Well, just, yeah, the number of digital inputs that you'll be juggling with your hands is going to be amazing. We do have a couple of questions for you, but before we get to them, what's the power budget for this system going to be?
That's a good question. The truth is, this was sort of napkin calculations, and these ideas are not fully fleshed out. So I don't know, actually.
Well, Matt McQuinn has an interesting thing that he points out in the Q&A. The 1 million FRB array that you are envisioning, lots of dipoles, is not so different from some of the high Z 21 centimeter observatories operating at 200 megahertz. So maybe the community can continue to piggyback?
Yeah, that's a good point. That's a good point. I think Larry Daddario did some costing analysis, and he said the sort of turnover in frequency when dipoles become more cost effective is of order 300 megahertz. So it's not so far from the EOR experiments.
Another from Jason Hessels, nice talk, Liam. Question, what kind of trade-off would you use in terms of number of FRBs versus time resolution you can search, given how that might affect the ability to do interesting applications?
Yeah, it's a fair question. I think if you need voltage data for the lensing stuff, which you do, then I think all you need to ensure is that you see the lensed copy and that you dump voltages. I think it's an open question what the intrinsic width distribution of FRBs is, and so how much you would get out of just searching to lower time resolution in terms of numbers. But I guess as long as you have voltage data, then you could at least do interesting stuff with the FRBs offline, including algorithms.
Yeah, but that's enormous caching or buffering requirements.
Yeah.
Something that came to mind when you mentioned something about tuning your search parameter space is, weren't you arguing just in the discussion session a couple of days ago that we shouldn't tune our searches because then we'll only find what we expect to find? Or was that maybe someone else was arguing that?
That was somebody else, and I have some sympathy for that view. But if we do this fairly targeted experiment where we're basically going after FRB applications to cosmology, and we want to maximize our detection of, say, FRBs in general or distant FRBs, then I think you really just need to apply what you know about the distribution.
Okay. Question from Sterl Finney. Bursts are much more valuable if they're localized to arcsecond precision. Do you see ways to achieve this?
Yeah, I think you could do outriggers. And again, I don't want to step on the toes of Wei Li because I know he's independently come up with a 1 million FRB machine kind of thing too, and he wants outriggers. But yeah, I think that would be important.
Right. Any other questions for Liam? If not, please add them to the Slack, and please join me in giving a round of virtual applause to all of the speakers in this session. Phenomenal set of talks. And then please join us in Gathertown whenever the next coffee break is scheduled for some more conversation. And see you all later then.